Good morning, everyone. Today I'm going to show you two videos. The first one is just doing the algebraic derivation of the relationship between orbital speed and radius or distance from the center object around which the object is orbiting. So that's just like what you did in part 3, but I'm going to show you the derivation. You can compare to what you got. And then the second video is related to just some practice problems. And the first question that I go through is actually the one on your worksheet. And then the second one is actually how we know the mass of the sun. So go ahead and watch those videos as you like, and I hope you all have a great day.
All right, I'm going to show you how to derive the relationship between the orbital speed and distance from the sun, just like you did in part 3. So this is what it should have looked like. First of all, we have our sun, and then we're talking about the orbital motion of the planets around it, or this could work for any solar system. So we've got Mercury, Venus, and Earth, and then, of course, there's many other planets and our sun. So the question is, how fast are these planets in orbit relative to their distance from the sun? Because they each have a different value for r here. And we know that their orbits are due to the gravitational force. So we have just the gravitational force and our net force acting on the planet. So I'm going to call that Fg on planet by the sun. So P for planet, S for sun. That net force is causing the circular motion. There's no other forces, so that's going to be our centripetal force. And then one of the things we've learned is that centripetal force is equal to mass times the centripetal acceleration, just like always, net force equal to mass times acceleration. And then this centripetal acceleration is given as the speed at which the object is rotating divided by the radius of its turn, so how sharp that turn is. All right, so we can recognize that Fg on the planet by the sun is our centripetal force, and that's going to be equal to the mass of the object rotating, so that's going to be the mass of the planet times its rotation speed divided by the radius. This gravitational force has its full expression of the gravitational constant times the mass of the sun times the mass of the planet divided by their separation distance squared. So we see we have another r here. And from here, we're just going to do some algebraic manipulation to simplify this. So first thing is that we could divide both sides by the mass of the planet. We'll notice that that's in the numerator on both sides. So if I divide both sides by the mass of the planet, doing the same thing on both sides, that means that the mass of the planet is going to cancel out on both sides. So this is completely independent of the mass of the planet. So that leaves us with g mass of the sun over r squared is equal to velocity squared over r. I'm also going to simplify my r's by multiplying both sides by 1 unit of r. So multiplying both sides by r. That means that here r divided by r is just 1, and here I can cancel one of the r's in the denominator. Okay, ultimately we're looking for the relationship between orbital speed, which is our velocity, versus distance, which is given as r in our equation, because that's the distance from the object that's rotating to the center of the rotation, the sun. So this is our y and this is our x. So I want the y value to not have this factor of squared. So I'm going to square root both sides, and we end up with just flipping the sides here, that v is equal to the square root of g times the mass of the sun divided by the radius of that orbit. The variables here are really the velocity and the radius. So one way you might want to think about this is that the velocity is equal to the square root of the gravitational constant times the mass of the sun. And then this is really maybe 1 over r square root of r, but let's say r to the 1/2 power. So if we put this into like a yx format, this is our y. So we'd have y is equal to, some constant. This is just a big constant. And then times 1 over x to the 1/2 power. So you might be wondering, what does this graph really look like? And one good way to visualize the graph is maybe to use a graphing software like Desmos. So I'm going to pull that up so that you can see what this graph would look like. Okay, so here I am on Desmos, and our equation was y equals some constant value. So we don't really care what that value is. It's going to be the square root of the gravitational constant times the mass of the sun, which would be the same for all of the planets in our solar system. So I'm going to leave that part out, but the function that we're trying to visualize is y equals 1 over x, and then to the 1/2 power. And here we are, we're seeing it. So anything that's 1 over x generally has this rational type of shape or inverse type of shape. And what that means in terms of our function, we're talking about y being the velocity and r being the distance. So let's consider the planet that's closest to our sun. That would be Mercury, so small r. Oh, it's going to have a higher velocity or a high orbital speed. And as that r gets larger and larger, we're going to see that the orbital speed actually decreases. And part of that would be related to the fact that the gravitational force is getting weaker and weaker at that further distance from the sun. And so instead of what we saw with our rubber stopper lab, where actually as the rubber stopper was further and further away, the velocity was still increasing. So that was our square root function. I could add that in here. So y is equal to, I don't know the square root function on here. So I'm going to use x to the 1/2 because that's the same thing. So in the rubber stopper lab, where the gravitational force was constant because we're still just on Earth, but as the rubber stopper was rotating it further and further, radii, we saw that the velocity still actually is increasing, just at a slower rate. However, when we look at the solar system, it's sort of a reverse or opposite effect, where the planets are moving faster the closer they are to the sun. And then what scientists can do is they can actually measure how fast are the planets moving, and then see how well this model using Newton's universal law of gravitation and centripetal, what we know about centripetal force, we can see how well it fits the model. So they've done this, and here's a graph that I found on the internet, so it must be valid. So sure enough, Mercury has the highest velocity in its orbital motion around the sun, and then going out, it's slower and slower, and sure enough, it looks like an inverse or rational function, and it's following that same function, that velocity or speed is equal to some constant times 1 over x to the 1/2, or the square root of that distance. So it holds true for our solar system. Now, next week, I'm going to have you watch a pretty cool movie that actually talks about where this relationship holds true in the solar system and where we've actually seen that it doesn't hold true. And that this led to the hypothesis that there's a lot more matter in the universe that we haven't accounted for. And this is the hypothesis that most of the universe is actually made up of what we call dark matter. And astrophysicists are still trying to figure out what is dark matter actually. It's one of the big questions that's still left unknown in the field of astrophysics, among many questions.